All right, so not all salts are actually soluble in water. There's a table here that's present in the book. I just copied and pasted it. It's in your textbook. It is table 4.1, and you should commit much of it to memory, so you can answer a few questions as to what happens if you throw a specific salt in water. So NaCl, for example, is going to always be soluble in water, and so if I put that in water, it will look soluble. It will look like this picture here. If I put something that is insoluble, does not dissolve in water, for example, anything that has OH minus, hydroxides, tend to be insoluble in water. So for example, aluminum hydroxide, if I put that in water, it will come out. It will not dissolve. It will not even come out. It will just not go in. It will just go to the bottom and say, I don't want this. I just don't like it. Sort of like sand in water. It just won't interact with the water. It will just go to the bottom. Okay, so to read this this table here, all the soluble ionic compounds, these are ions that we're going to be discussing. Primarily, we talk about solubility because salts are ionic. Compounds that contain these ions they tend to be soluble in water. So anything that has a nitrate or an acetate will dissolve in water. There are no exceptions. Most things that have chlorine and bromine and iodine are going to be soluble in water. So all chlorides, unless they are silver chloride, mercury chloride, or lead chloride, or silver bromide, mercury bromide, or lead bromide, same thing for iodide. These things will be insoluble in water. Anything else, NaCl, whatever, and magnesium chloride, whatever, they will dissolve in water. Sulfates will be soluble in water for the most part, with these exceptions. Okay, these are largely insoluble, and so the exceptions are here to show you which of these exceptions are actually soluble. So sulfur-containing ions tend to not dissolve in water unless they are of ammonium. So ammonium and ammonium sulfide will dissolve in water. For example, carbonates tend not to dissolve in water unless it is ammonium carbonate, or the first group, sodium and so forth, lithium and all that. If they are associated with a carbonate, they will dissolve in water. Aluminum carbonate won't, but sodium carbonate will. And so on. So that's how you would read this. And so let's look at a few examples of this. Here we'll look here. If I have lead sulfate here, lead sulfate. So this is going to be a little bit of a practice into like how to write these chemical formulas as well. So lead, as a reminder, is Pb. And lead, I should have written this as lead 2. It's lead 2 sulfate, then I have lead plus 2. Sulfate is SO4 minus 2. They are balanced, so I don't have to write this. And basically, lead sulfate does look like this. Lead sulfate. And the question is lead sulfate soluble or not? So if you go back to our little table here, I'm going to go under sulfates. Here, sulfates are indeed always soluble unless they are the sulfates of these 4 ions. And so lead is here. So lead sulfate is actually insoluble. So insoluble. All right, let's look at barium carbonate. Barium is got a charge of +2. The carbonate is CO3 minus 2. Again, they're balanced, so I can basically just kind of combine them together, and it looks like this, barium carbonate. And is barium carbonate a soluble or not? Well, I'm going to go here and look at the carbonates. Carbonates tend to be insoluble unless they are of the alkali metal cations, and barium is not, unfortunately. Right? It's group 2, not group 1, and therefore barium carbonate is insoluble. If it was sodium carbonate, it would be soluble, but it is not. Here, lithium phosphate. Lithium is Li+. Phosphate is PO4 minus 3. I'm going to crisscross, so I will need 3 lithiums. and 1 phosphate, and to form this thing. And is lithium phosphate soluble? Well, let's look. Phosphates tend to be insoluble unless they are of the alkali metal cations. Lithium is an alkali metal, and so it is an exception to the insolubility. It is soluble. So this guy is soluble. All right, sodium nitrate. Sodium is Na, nitrate is NO3 minus. So you can just write it like that. Nitrates are here. They're always soluble. No exceptions. So that's an easy one. Just memorize that nitrates will always dissolve. There are no exceptions. Okay, strontium sulfate with this 2 here telling you that strontium is +2. So it would be sulfate is SO4 minus 2, so they will balance. You look at sulfates here. Sulfates are soluble unless they're paired with strontium, barium, mercury, or lead. Therefore, this is insoluble. Okay, this is how you go about doing this. Potassium hydroxide. Potassium is K, hydroxide is OH. Potassium hydroxide, well, that's going to be soluble because all hydroxides are insoluble unless they're with group 1A or ammonium, and calcium, strontium, barium. And potassium is indeed group 1A, and so KOH is soluble. And lastly is aluminum hydroxide. Aluminum is +3. Hydroxide is -1. I'm going to crisscross that, and so I have 3 here, and well, 1 here. This is aluminum hydroxide. All hydroxides are insoluble unless they're group 1A and ammonium, calcium, strontium, and barium. This is not any of those exceptions, therefore this is insoluble. Okay, so that's how you would do this type of thing. So hopefully that made some sense. That's just to predict what happens if I have a vial of a salt and I want to know what happens if I put that in water. Okay, so that's what you would do. The way practically we see this precipitation thing happen is when I have multiple salts interacting with one another. So maybe I have 2 things that dissolve, but when I mix them together, I happen to force something that doesn't dissolve and it comes out. That's usually what occurs in chemistry in engineering when dealing with any processes. So let's look at this type thing. So if I have 2 salts added to water, the 2 salts can interact. So if I have AB, that's a salt, and CD, that's another salt, again, this AQ tells me that A and B dissociate into A plus and B minus. And CD aqueous means that they dissociate into C plus and D minus. Now nothing, they're all together, they're all hanging out. Maybe A can go hang out with D, and B can hang out with C. So I can actually form AD and CB, whatever, why not? If AD or BC are on that table that we just looked at, and they are predicted to be insoluble, well then I will see it come out. This will happen, it will precipitate. So if this is AB, this is CD, and I mix them together, let's say, well, BC is insoluble, well, BC will start coming out. That's what you'll see. It will become cloudy, and then it will start raining or precipitating. That's what we're calling it, precipitate. It will come out, and eventually, if you leave it well enough alone, eventually it will just settle to the bottom, like that picture I showed you. Look at it here. It will look like that eventually, right? So that's that. And again, it looks like snow or rain, and so we call it a precipitation. So it's a precipitate. All right, so here are some visual precipitates. Some of them are very pretty. Some of them have different colors. Some of them are not as heavy, and so they float or whatever. How do we go about practically figuring this out when you mix 2 solutions together? Let's do an example through PowerPoint, and then we will do one on the whiteboard and see how to do that. Okay, so suppose I have a solution of silver nitrate, okay, and I mix it with sodium chloride. What happens then? And so I did this on purpose, so obviously it's going to precipitate, but silver nitrate is going to be a soluble salt if you look at the table. Sodium chloride is a soluble salt. So they look, or initially they look like this. They look like just regular water. They have a salt inside. So what happens when I mix them together? Okay. So if I put AgNO3 and NaCl in water, I will start forming these ions: Ag plus aqueous, NO3 minus aqueous, Na plus aqueous, Cl minus aqueous, so on and so forth, right? Now, Na doesn't have to interact just with Cl. It's an equal opportunity ion, so it will interact with NO3 minus as well. And Ag plus will also interact with Cl minus. And if you look at the table, silver chloride is insoluble. Okay, so what you're actually going to see is that when you have these four ions together, actually AgCl will start, whenever Ag and Cl see each other, they'll be like, hey, we don't like this, and they'll come out. NO3 minus and Na plus still like being dissolved, so they'll stay dissolved. But AgCl will start coming out, and you'll start seeing a precipitate of silver chloride falling down in your vial or in your cup or in your beaker, wherever you're mixing this stuff. Okay, now I will point out, if I'm looking at this equation, what chemists tend to do is cancel out anything that shows up on both sides. I've talked about chemical equations before, calling them equations, that they are similar to mathematical equations. Yeah, they are similar. This, you can act sort of like as an equal sign, and if in math I have something that's appearing on both sides, I can just cancel it out. Well, in chemistry too. So if I have NO3 minus on this side and NO3 minus on this side, well, I can cancel it out. These are called spectator ions. They're just watching. They're not actually doing anything. They're just watching. So NO3 minus will cancel out NO3 minus. Na plus will cancel Na plus. And what I'm left with is silver ion plus chloride ion will form silver chloride precipitate, and it will come out, right? These three equations have names, and you should know them. This is known as the complete ionic equation. Okay, I will have the ions that I'm dissolving. I can replace these four with these two. It's the same thing, and I will form the precipitate and the two things that stay dissolved. The complete ionic equation has all the spectator ions in it. Nothing got canceled out. It has a precipitate in it. It has whatever started with is in it. That's a complete ionic equation. Once I cancel out all the spectator ions, I'll be left with only the stuff that got actually reacted, all the stuff that actually has some dynamics, anything that makes any sort of interesting sense, and that will be known as the net ionic equation. It has no spectators in it, and so you can see only the things that did stuff are in the net ionic equation. And also, a dissociation equation would be the stuff you had at the beginning and it dissociating into ions. So that we just talked about that earlier too. So you should know these three. These you'll be asked several times to come up with a net ionic equation or the complete ionic equation when you're mixing two things together. This will work for acids and bases and ions and other things. So this extends beyond this chapter. Right, so let's look at an example of mixing two solutions together. And so I want to know what happens when I mix. What happens if I mix potassium phosphate? Okay, and it's going to be aqueous. So I'm going to show you the beginning of this. That I'm not even showing you the dissociation. I'm mixing potassium sulfate and calcium nitrate. The question is, what happens? I want to know what happens when I'm mixing these two. Okay, so I want you to write the net ionic equation and identify the spectator ions. All right, so what we'll do first is, let's write the dissociation. All ions will dissolve at first, right? All ions show this a dissociation into the water. So K3PO4 aqueous plus calcium nitrate. When I throw this in water, I will form K plus aqueous, and I will form phosphate. and I will form calcium ion, and I will also form nitrate. Okay, I'll form all four ions that way. This is known as the dissociation equation right here. And like I said, potassium can interact with phosphate, where its original friend, or it can interact with nitrate, and calcium can interact with nitrate or with phosphate. And if that actually happens, if they do go around and intermingle as they do, if you look at the solubility guidelines, so let me pull that up so we have it. Let's look at that. Oops. If I look at this thing here, let's look what happens. So nitrates are always going to be soluble. So it doesn't really matter here if it's potassium and nitrate together or calcium and nitrate together. That's going to be soluble. The trick here is to figure out what happens with the phosphate, because phosphate is the one that's going to give us any trouble. Phosphate tends to be insoluble. But potassium phosphate is soluble because it's an alkali metal. But calcium phosphate, that won't be. That will not be soluble. So what happens is that the calcium here, is going to interact with the phosphate and precipitate out. So we identified that calcium phosphate, this thing, is insoluble. Okay, so this is what's been identified. So I'm going to identify that right here, and I'm going to rewrite this and identify what dissolved and what precipitated out. Okay, aqueous, and this will form, well, it will form calcium phosphate, which will dissolve as that will not dissolve as we just identified as a solid, and it will also form K plus and NO3 minus aqueous. Okay, they will both hang out there as dissolved ions. Now, I'm going to balance the equation. I didn't ask you to, but I will balance the equation. And when you balance this, you get 2 of this plus 3 of this. And that will form 1 of this. It's just good form to have them balanced, and 6 of this. Okay, so that's what occurs. Now we can recognize again that K plus, this K here, and the NO3 here, there are spectator ions. They are not going to interact. This K here and the NO3, they're going to be spectator ions, and I can cancel them out. So this thing here, we just wrote this entire thing here in blue. This is going to be my complete ionic equation. And when I cancel out the stuff I highlighted in red, the spectator ions, I will be left with my net ionic equation, which is going to be 3Ca plus aqueous plus 2PO4 minus 3 aqueous will form 1Ca3PO4 aqueous, not aqueous, sorry, solid, because this did not dissolve. And this here is my net ionic equation. Okay, so this is how you go about doing this. You just have to identify them and just follow through. This may have looked a little more challenging. I did it on purpose, and the only challenge came about because I balanced it, because I have to balance stuff. Okay, so that's how you go about that. I think that's it for now. Next little section will be acids and bases.